All right, so the first piece of evidence was the fact that the asthenosphere, or asthenosphere as some pronounce it, is confirmed. Now, remember that the asthenosphere is that elasticy layer that has both properties of a solid and a liquid that lies beneath the lithosphere. The lithosphere is solid, that's our crust. And then the asthenosphere kind of acts like silly putty or a very thick slime, where it has different properties than a liquid or the solid would have. So recall that the seismic data that allowed us to determine the composition of the layers of the Earth showed that, in fact, the seismic waves, both the S and P waves, sped up when they reached this material, or rather slowed down, because recall that seismic waves move faster through more compressible materials. So in the crust materials, they moved fast. And then when they reached the asthenosphere, because it was less or more compressible, I hate those terms, more compressible, meaning less solid, it slowed down the waves, okay, and it made them bend. So also recall that the asthenosphere is very important in the idea of continental drift, because without some kind of an elastic layer, the continents would be simply on some type of hard surface. So the asthenosphere is very important.
Like it's cutting out.
I am cutting out.
Yeah, just like whatever the last thing you said was.
Okay, I wonder, okay. We'll keep going, and if there's stuff that cuts out, I will make sure I post this lesson, the slides in Classroom, so you can fill in stuff. So that was the number one here.
It's happening again.
Not good, huh? What to do, what to do, what to do. All right, what I'm gonna do is I'm gonna share my speaker notes. That way, if you can't hear, you can at least see the notes up here. And this is the slide we're talking about, okay? Not perfect, but at least you can see the notes then, okay? I will keep talking, and if you can't hear it, just read the notes and take the notes from there. Okay, so hopefully you get some of that. I'll leave that out there for a second. Okay, number 2 piece of evidence was earthquake distribution. So there's a lot of earthquakes around Japan, and a Japanese scientist, Kiyu Wadato, suggested that maybe those earthquakes and volcanoes were related to this idea of continental drift. And he thought it might be direct evidence of big slabs of the Earth's crust moving. Whoops. Okay, so this all relates to earthquakes. Around 1940, they began to plot these earthquakes to see if there was some type of pattern. And you will notice that around the outer edges of the Pacific Ocean, there are quite a large number of earthquakes. And this area became known as the Pacific Ring of Fire. This is an area of very heavy volcanic activity. Which is believed to be was believed to be a sign of plate movement or continental drift. Now, an interesting fact that even though there's only 1,000 earthquakes plotted on this slide, there are more than 1 million earthquakes a year of varying magnitudes. Okay, we can't feel all of them, but the earth is still very active. Just looking at the area of Nevada and California in our own country, this was earthquake data from just 1 week in September of 2018. There were 686 total earthquakes during that time of various magnitudes. So the point here basically is just that the movement that Wegener proposed is still going on today, and there's plenty of evidence to support it. So as a side note, most of you have probably heard of the Richter scale. So the Richter scale is how we measure, it's how we measure earthquakes. Okay, so Richter developed a scale that could measure the magnitude of earthquakes. So basically what he did was he looked at the difference in arrival times between the S and P waves and how big those S waves were. If you remember from the gizmo, the really big ones showed a really major earthquake. So he gave a magnitude for the disturbance, and the Richter scale runs between 1 and 10 or 1 and 12, 1 being the weakest, 12 being the most catastrophic earthquakes. The highest magnitude ever recorded was 9.6 in Valdivia, Chile in 1960. There was a pretty major one in Alaska as well. So you don't need to know details of the Richter scale. You just need to recognize that the higher the magnitude, the stronger the earthquake. Just to give you some reference, here's a list showing what the equivalent power is or energy of an earthquake is. At 12, which is the highest possible, that would be enough energy to split the earth in half, basically run a fault right down the middle. So if we have a 12, it's nothing. But even a 4.5 is like a tornado. Okay, so that's a pretty good amount of energy. A 1, you probably can't really feel. A 2, you're just barely starting to feel. Okay, back to evidence. So evidence number 3, the shape of the ocean floor supported the idea of continental drift. So even though the Challenger expedition did enough bottom mapping using weights and ropes to show that there was a ridge in the middle of the Atlantic Ocean, it wasn't until the detailed data after World War II came out, echo sounders, that it came to light about this mid-Atlantic ridge. The mid-Atlantic ridge runs down the middle of the Atlantic, and there are other ridges in other oceans. And this ridge seemed to support that something was going on in terms of the continents because it falls directly down the middle. So that seemed like too odd a coincidence for it to not have something to do with the continents. This is what an echosound mapping looks like of the ridge. On the sides, we have the continents. Continents are on the sides. And right in the middle of them is what looks like a mountain ridge, but there is a rift in between. A rift is just a very deep gap. And this is known as a rift valley. We'll talk more about those rift valleys. Here's kind of a more general look at what it looks like. Okay, number 4. This is, wait for it to come back. There we go. This is the radiometric dating of sediments, which supported the idea of continental drift. So what is radiometric dating? Well, that's using basically nuclear decay and the radioactivity given off to determine the age of sediments. And what they noticed was that the sediments, which basically is the loose, not dirt, but the loose particles lying on top of the bedrock at the bottom of the ocean, they noticed that this was way younger than the bedrock rock itself. Okay, so what this told them was that new ocean floor is being formed from somewhere. The maximum age of the sediments that lie on the bedrock is 200 million years. Compared to the age of the Earth, or the continents, which is about 4 billion years old. So this just kind of shows you how they're able to use echo sounder data to see the sediment lying on top of the bedrock. And this brings us to our next slide. Okay, we're going to stop there. This was a really frustrating session. Was everyone able to get enough out of that by looking at the notes from my slides? For the most part? Okay, I'll answer any questions the next class we have to make sure everyone gets those filled in. Unfortunately, this is the session I usually record on Zoom. I don't record my first period, so I don't even have a good Zoom recording for you today. So I'll post what I have, but it's probably not going to be that helpful. I will post these slides though for you so you can fill in any missing info. All right, I will see you guys tomorrow then.